Welcome to Get Your FRQ On. This question is from 2001. It is question 3 and it is calculator active. In the question stem, we are given that a car is traveling on a straight road. At t equals 0, the velocity of the car is 55 miles per hour, and we are given a graph of a of t, the acceleration of the car, at time t, and the graph of a of t consists of nothing but line segments. In part A of the question, we are asked if the velocity of the car is increasing at t equals 2 seconds, and to explain why or why not. Calculus tells us that the velocity of the car will be increasing at t equals 2 if the rate of change of the velocity is positive at t equals 2. We don't have a function for v of t, but we do have a function for a of t, which is the derivative of v of t. So, at t equals 2, the function that we're given for a of t, well, the value of a of 2 would be the derivative of v at 2. It would be the rate of change of the velocity at t equals 2. And according to the graph, a of 2 is 15. Since a of 2, which is 15, is greater than 0, yes, the velocity of the car is increasing at t equals 2. In part B, we are asked if the velocity is ever 55 miles an hour for values of t not equal to 0, between 0 and 18, and then also to explain why or why not. All right, we are given in the question stem that the velocity at t equals 0 is 55 miles per hour. So really what this comes down to is there ever a point where the net change between 0 and some other value of t between 0 and 18 where that net change is 0? If there is, then the car's speed must be 55 miles an hour at that point in time because the net change is 0. All right, so it would have to be the case that v of t minus v of 0 is 0, and that definitely looks like a problem for the fundamental theorem of calculus. All right, so we know by the fundamental theorem of calculus that v of t minus v of 0 is the integral from 0 to t of a of x dx. Now notice the change in variable here. We are integrating from 0 to some time t, so the variable in our function must be different than t. It doesn't make a lot of sense to have the integral from 0 to t of a of t dt. So we do have to make that change. Be careful about that. Based on the graph provided for a of t, that difference will be 0 when t is 12 seconds. Right? And then note that this is true since the integral consists of two congruent trapezoids. At least it does from 0 to 12. One of them is above the x-axis, one of them is below the x-axis, so one of them counts as positive net gain, the other one counts as negative net gain. But since they are congruent, they have the same area. One is positive, one is negative, so they cancel each other out. So at t equals 12, that total net area there would be 0. So at t equals 12, the car is also going 55 miles per hour. What is the car's absolute maximum velocity on the interval from 0 to 18, and when does it occur? All right, we know that by the extreme value theorem, the absolute maximum must occur at either an endpoint or somewhere in the interval from 0 to 18, where v prime of t is equal to 0, v prime of t is also equal to a of t. So we're really just looking for somewhere on the graph where a of t is equal to 0. Okay? We're given in the question stem that v of 0 is 55 feet per second. Okay. A of 6 is 0, right? We get that from the graph, so we need to find v of 6, and then also v of 18, since 18 is another endpoint. All right, so v of 6 we can find by using the fundamental theorem of calculus again. That would be 55 plus the integral from 0 to 6 of a of t dt. And that integral, because it's all line segments, we should be able to calculate that by hand by using rules for trapezoids and things like that. All right, so 55 plus, taking into account the relative heights of the function that we need, 1/2 times 15 times 2 plus 6 ends up being 115 feet per second. All right, so at t equals 6, the velocity of the car is 115 feet per second, which is more than 55 feet per second. All right, so we know that v of 6, t equals 6, could be the maximum when it occurs, and 155 might be the maximum velocity. Just got to check v of 18. V of 18, we can do the same way, 55 plus that integral. So we take into account the fact that from 0 to 6 it was 115. Notice after that the values of a of t are all negative for a while, so we're going to get some negative area here. A lot of stuff gets canceled out that we gained for v of 6, and ultimately v of 18 turns out to be 25 feet per second, which is definitely less than 115 feet per second. So what we can conclude here is that the maximum velocity of the car is 115 feet per second, and it occurs at t equals 6 seconds. In part D, is there a time between 0 and 18 seconds when the velocity is 0? Justify your conclusion. Well, we know from the previous part that the maximum velocity of the car is 115 feet per second when t is equal to 6. The absolute minimum velocity of the car would have to occur when either t equals 0 or t equals 18, since there's no other place where a of t is equal to 0. All right, so, or somewhere else where a of t is equal to 0. So we either have an endpoint or some other 0 of a of t. All right, well, from the graph of a of t, the only other time when a of t is equal to 0 is t equals 16 seconds, but we can use the fundamental theorem of calculus to evaluate what v of 16 is. All right, so v of 16 is 55 plus the integral from 0 to 16 of a of t dt, and when we evaluate that, we get 10 feet per second. Now, here's what's important about that. This is the absolute minimum velocity, and it's positive, which means the car is never has velocity 0 feet per second. All right, so since the absolute minimum velocity of the car is 10 feet per second, 10 is greater than 0, no, the velocity of the car is never 0 feet per second.